Recording is rolling. It's Wednesday, January 21st. We're going to do two lessons in one today, and then we're just going to take the rest of the week to focus on these. So 8.1 and 8.2 in your book talks about logarithms and then properties and things you do with logarithms. Okay, so what is a logarithm? What is it good for? There are two logarithm keys on your calculator. You might know that. They're near the top left, right? One says log, right beneath it, there's one that says ln, which is also a logarithm. It's just the natural base c. Right? So what do you think? So I think historically, I remember you go back hundreds of years ago, there were these like books of published logarithms that you could buy. And what you could do is you could like multiply numbers, but instead of multiplying, you're adding, right? So one useful application of logarithms is that exponents become multiplication, multiplication becomes adding, right? So math is a little different, right? But also you can take values that have wildly different orders of magnitude, and you can crunch it down to something that's a bit more manageable, right? So I'll do some examples with you guys of like earthquake magnitudes and sound levels, and you can even bring in interest rates with time, right? And money accumulating interest. Right? There are applications to all those. Anything that you can express as a power, right? You guys see this right here. You can rearrange it into a logarithm form. Okay? Sometimes I hear this called rolling the log. I don't know if that phrase would show up in the map, but a lot of people use it. So it's taking one form of an expression, it's just re-expressing it a different way. So here, I'll show you guys some examples with this, some real basic examples. Now, I've pre-recorded, guys, I pre-recorded like over an hour and a half of examples, just a ton of examples, some textbook examples, some story examples, and those are already uploaded to Google Classroom. They've been up there a couple of days. Okay? But today, right in front of you guys right now, I just want to do some very fundamental examples, show you guys some basic graphs, show a couple story examples, right, and then get you guys going on your way. Okay? The next Alex assignment is also open. It's 8182. Right? Right. So let's look right here. Let's say you had some exponential. Right? How could you re-express this, and what would this look like? So what if I have 10, I'm going to just start with base 10, okay, to the power of 5. Okay. Guys, what is 10 to the power of 5? If you expand that out, what is that?
No, or not 100.
Yeah, it's under 100,000. Right? You got calculators, you can try it out. That's right. Got 100,000. So 100,000, right? 100,000. Great. How about this? Um, what is 10 to the power of 6? What is that?
A million?
Yeah, a million. Right. Huh. Okay. So you see by changing the power by one, the actual value expands by a whole order of magnitude, right? That okay. Okay, so what if you wanted to think in terms of these powers? Okay? Well, that's what we can bring in these logarithms. Okay. So so look at this pattern here, and really best way to learn this is just to do a bunch of examples from the book. Okay. But we have some base to some power equals something. Okay. So I can rewrite that as log base this value. So let me go over here and use my example. So if I do log base 10, and if you just have the word log, it's almost always implied to be base 10 anyway. Right? But I take the base 10, right? Of the other side, like so of the answer, so 100,000 for this example. Okay. And that should be equal to this power. Ooh, okay. So remember like back in module 7, sometimes you saw some puzzles where you're supposed to solve for x, but x is buried in the exponent. So how do you get it out of the exponent? And there were some kind of fancy ways for some very special cases back in Mod 7. But this is a more proper way to do that. Notice that what used to be in the power is no longer in the power. You guys see that? That's interesting. Okay. And what about the calculator? Guys, let's confirm this on the calculator. So you guys got this model calculator. So hit log. Again, that's base 10. It's already applied to be base 10. We'll look at the other bases later. Okay. And then type in 100,000 and then close parenthesis. Okay. And when I hit enter, what do you think the calculator is going to say? 5? Yeah, it sure does. 5 right there. Is it? Right. How about this? All right. Can you rewrite this one as a logarithm? Right. So 10 to the 6 is a million. That's okay, right? Okay. How can I write that in logarithmic form? Log base 10 of what is equal to what?
Million and you put a six.
Yeah, of a million should be equal to 6. Okay. Let's see if that's what the calculator says. So log of 1 million. Yeah, it is 6. Just like that. Like I said. Right. Oh, let's look at a story example of this. You guys know about earthquakes? Earthquakes? Okay. So if you do 10 to the power of the, well, I'll call it R equals I. Okay. So R could be the Richter scale reading or not number. Uh, okay. And I refers to the relative intensity of the earthquake. Okay. You guys see that the two examples that I set up exactly follow this model? You see it? Right. So um, let's put this in log form. Okay. So log base 10 of what is equal to what? Of the actual intensity will tell you the Richter scale number. Do you guys see that? Okay, so kind of separate out my examples here. Yeah, that was a little better. Okay. Okay, so guys, what if you hear that there was some earthquake and it has a magnitude 5? It was a magnitude 5 earthquake. Okay, you guys get that? Okay. That 5 refers to this R. Okay. Then you hear, oh, there was actually another earthquake that's a magnitude 6. Guys, if you go from a magnitude 5 quake to a magnitude 6 quake, how many times more intense is the 6 compared to the 5? 10 times. It's 10 times the intensity. Is that? What if there was a magnitude 7 quake? How would that compare to these? It'd be, yeah, 10 times the magnitude 6. And how many times the magnitude 5? 100 times. Okay. So if I say magnitude 7 quake, you say, oh, well, 7 compared to 5, well, that's only a difference of 2. No, that's an order of magnitude of 2. That's like 10 to the power of 2. Yeah, which would be 100 times. So a magnitude 7 quake, I'll spell it up. A magnitude 7 earthquake is 100 times, because that's 10 to the 2, more intense than a magnitude 5 quake. Yeah, all right. So we're looking at orders of magnitude here. Okay, you guys can see that? Right. Another story example here, but I got this within reach. Is decibels to represent sound intensity level. Okay, is look at like how many decibels correspond to like, these story examples. Right, so if you whisper to your friend and maybe no one can hear you except for your friend because you're whispering so quietly, okay, that's roughly 40 decibels. Think of it like that. Okay. If you're talking like I'm talking right now, I'm probably talking pretty close to this right here, about 60 decibels. Okay. If you play really loud music, that's like 80 decibels. And threshold of pain, where the air pressure is such that it's about to tear your eardrums apart and cause permanent, like, that's like 120 decibels. Okay. Now, the numbers themselves, like, okay, 40, 60, 80, 100, well, 60 to 120, is that double? It's like, no, it has nothing to do with it. Okay. We're talking about orders of magnitude that are different, kind of like Richter scale ratings too. Okay. And oh, what do I see here? I see a log. You guys see a 10 times log or something? You guys see it. Okay. I do want to show you guys graphical versions of these because you might be able to see this from this box. What I'm about to say is that logarithms and exponents, in terms of graphs, are really inverses of each other. Right? And you guys remember what inverses look like, right? Oh, oops, I got it up here already. Here we go. Right. So this, well, let's start with the blue curve actually. You guys see y equals 10 to the x. We've been working with exponents for a few weeks now, haven't we? Right. So 10 to the 0 is 1. 10 to the 1 is 10. That's right here. 10 squared is 100. That's way up off the screen. You guys see that? Okay. And create this curve. Okay. Seen a lot of those. Okay. Well, if you rewrite this in log form, so I swap the x and the y, okay, then you'll get this red one. Okay, so y equals log base 10x. Okay, and that looks like this. Do you guys remember we did inverses last semester? And one way to spot inverse on graphs is if you create a line y equals that here. I'll even dash it off here and say y is equal to x. Okay, see that 45-degree line right there? If that was a mirror, couldn't you translate one graph from the other across that mirror? Right, hence those are inverses. Okay, let me show you guys something else that's pretty cool. What if you here? I'll just throw it up here. What if you wanted to change the base? Let's do y equals, now if I do log and then underscore, and I'm going to change the base from uh, 10 to e. Right? You guys remember e, that 2.718 number, very special number of x. What does that look like? What color did it give me here? Purple? Okay, yeah, you guys see that purple curve? It's a log curve, but maybe it's less extreme than log base 10 because e is only 2.718. Okay. And then the inverse of that would be like y equals e to power of x. Let's see what that looks like. Yeah, that's that black curve. You guys see the black and the purple are inverses? You guys see that too? Okay. But there's a different way to write log e because log e, like e is such a common base. It is such important applications of math. That's the other log key on your calculator. It's called natural log. The one that says ln. And so Desmos will recognize that. Guys, if I just change this log base e to ln, look, it creates the exact same curve. It didn't change. Is it still a purple curve? Yes, I do. Right. All right. You guys good so far? Good. Okay. So we have the premise of logarithms. Right. You're looking at the graphs. Right. So you guys see the graphical relationships. You see that logs and exponents are inverses. And if you have an exponential equation, you can express it as a logarithm. And here's some examples how to do it. Okay. You guys good so far?
Yeah.
Okay. That's pretty much 8-1 in a nutshell. But I want to show you guys some other stuff you can do with logarithms. Okay, and that is here. Oh, here we go. Okay, I got this whole page of rules. Okay, again, we're multiplying two numbers. If you put it in log form, you can actually add two different logarithms. Okay, division turns into subtraction. A power turns into multiplication. And there's also a way to convert bases. Okay, so I'll show you guys examples of all of those, and then at that point, I think you guys be able to answer any question on Alex or in your book. Okay. So what if you have, let's stick to log base 10, right? So log of, how about 4 times 7? 4 times 7. Okay. So according to this rule right here, I should be able to express that as what?
Log 4 plus log 7.
Exactly. Log 4 plus log 7. Okay. Let's see if that's true. I mean, I'm claiming that's true. So if I have in my calculator log of isn't 4 times 7 28? Is that okay? Okay. Let me see what it is. So that's 1.447. Well, I'll cut it off at some point. It's pretty, I'm rounding a little bit. Okay. Is that equal to this plus this? So log 4, this by itself could be 0.602 roundabouts. And log 7 is 0.845. Let's see if I add those two together. 0.845 plus 602. Okay. 1.4. Yeah, it's the same thing. Check. Bing. It checks out. Guess that? Oh, yeah. Okay.
Would you only do this to clean up the equation? Like if you said log 4 plus log 7 plus log 3, you could just put it all into one log.
Yeah, right. You could go back and forth. It depends what you're trying to do, like what you're trying to solve. Right? So if I had this on the left, I could expand it out to the right. Or if you start with this on the right, separate logarithms added, you could totally add them together and multiply the numbers together. You could do that too. Yeah. Instead of 4 and 7, it might be like 4 and x or x and y. Yeah, sometimes there are variables that show up. Yeah, but all these rules apply. Okay. All right. Division in terms of subtraction. So let's do that. What if I do log of well, let's do 4 over 7. 4 over 7. Okay. So that should be log 4 minus log 7. And it looks like the way it shows this, actually, you know what log 4 and log 7 are? They're right here. It's decimals. Okay. Okay, so if I take a small decimal minus a big decimal, should I get a negative number?
Yeah.
Negative? Huh. Hey, does that mean if I take a log of a fraction between 0 and 1, I also get a negative number? Let's see if it is. What's log of 4 over 7? It is negative. Yeah, it's negative 0.243 something, something, something. Right? Separate my examples here. Right. Yeah, that could be the difference of those. I think that works. Okay. Check. And you can see that on the graph too. Let me remind you guys with the graph. Right? Here's, remember these logarithm curves. Well, one of them's in purple, one of them's in red. The same basic shape. You guys see, like, once you go to the left of 1 between like 0 and 1, right? You get negative values. Right? I meant to point out too. Do you guys see some domain and range restrictions on these types of curves? Right? Like back to the exponentials we've been working with for a few weeks. There was no domain restriction, but there is a range restriction. Right? Y has to be positive. Right? With logarithms, since those are inverses, the opposite is true. There's a domain restriction. X can only be positive. Like, guys, can you take a logarithm of a negative number? No, right? That'd be like saying, like, oh, what if there was an earthquake with negative intensity? Well, that wouldn't really mean anything, right? Or okay, what someone's talking with negative loudness? Like what? Right, right. But there is no range restriction, right? So once you take that logarithm, the logarithm itself could be negative or positive. That's okay. You can only take logarithms of positive values, though. Okay, and you're seeing it right there. All right. So, okay. So we got this product type rule, we got this quotient type rule. Uh, let's do powers become uh, products. So that's it. So if you have logarithm of, I'm saying a to the power of b, the rule is you're allowed to take this power on a, which is b, and you can move it in front and multiply it. So let's do log of 4 to the power of 7. Log 4 to the 7. Okay. Now I'm claiming that's the same thing as, guys, how can I, sorry, subject. Guys, how can I write this in maybe an expanded form? Equal to what?
7 times log 4.
Exactly, 7 times log 4. Right? Let's try this out on the calculator. I should get the same thing. What's log of 4 to the power of 7? It's a, okay. Yeah, actually, that's not even that big. It's 4.21 something. Okay, so this right here is like 4.214 something something. Okay, it's the same thing. 7 times log 4 okay, is also, yeah, 4.214 something something. Yeah, check. It's the same thing. Okay, check these to go along. Um, okay, here's one more main thing I want to show you guys, which is you can change base. Because I've been mostly sticking to base 10. Guys, these are all base 10, right? The log key on your calculator is implied base 10, or it is base 10. Right? But there's a different case that's ln, that's for natural log, right? And that's base e. But you don't have to necessarily have 10 and e as the only bases. Like this x, you can take anything to an exponent. Right? So what if this base is like something weird, right? Like pi or 5 or whatever. Right? How do you, right? So if you have some strange base, you can handle that by changing to either base 10 or base e. I'm showing here. Actually, this is kind of small. I'm going to write this bigger. Log base b of a is the same thing as log base 10 of a over log base 10 of b. Okay. But it doesn't have to be base 10. It could really be any base. So, for example, natural log of a over natural log of b. Okay. Let's try that with how about 4 and 7? Okay. What if I'm going to do log base 7 of 4? Let's try that. Okay. So I wonder what that is. Okay. Another way to say that, if I call that equal to x, okay, here, let's go back to the beginning of today. How can you write this as an exponent? 7 to the, here, look at it right here. X to the y equals z, right? X to the y equals z. So 7 to the power of what? X is equal to 4, right? And we'll round back around. We'll see if this is true. Okay? Now I'm claiming that you should be able to do this with it. Like for example, natural log of 4 over natural log of 7. Okay? So let's get a decimal approximation. Then later on I'll plug that decimal approximation in for this x, and we'll see how close to 4 this becomes. Let's try this out. So what is natural log of 4 divided by natural log of 7? Okay. So I'm looking at approximately 0.7124 something, something, something. Yeah. Okay, so let's plug it in right here. What is 7 to the 0.7124 something, something? Okay. Is that approximately equal to 4? Okay, let's see. 7 to the power of 0.7124. 3.9999. Yeah, I'll call it 4. Bing. Here, a win. Okay, you guys got it? Okay. All right, so first I read you guys' Alex questions, and one of the questions I saw coming up was they said, could you expand like a crazy looking right? So for example, what if you saw log of let's do a times the square root of b all divided by c. Right, I think that would be pretty good. Right? Can you express this? Can you expand this into logarithms? Right, like using the set of rules that I was just taking us through. Okay, okay. So okay. I can say this is the same thing as log. Okay, guys, how should I finish this off? What should I put right here?
C.
Let's try it. I'm going to start with this log a right here. Okay. Now, if I'm multiplying something inside the logarithm, that means I actually want to do what to two separate logarithms? Add them. Yeah. So I'm going to say plus log of the square root of b. Okay. And then when you're dividing inside the logarithm. That means you can do what to two logarithms? Subtract. Okay, so minus log of c. Okay, so this is this, but we can actually go further. Okay, guys, what is the square root? What is the square root as a power? Guys, the square root of b is equal to b to the power of what? 1/2. Yeah, 1/2. Okay. So if you know that, then oh, that's looking a lot like this row right here. Isn't that this row right here? Here, I'll expand out the next one. Right, so what I'm saying is this is what I'm imagining. Plus log b to the half power minus log c. Okay. Okay, so there's still one more step I can do that Alex would probably want you to do to get full credit on this, and that's what do you do with this 1/2 right now?
Put it on the log.
Exactly. So now I got log of a plus 1/2 log of b, and then minus log c. Right? And you can come up with any numbers you want for a, b, and c, like 4, 7, and 10, or 5, 9, and pi. Right? And this expression and this expression are the same thing. Yeah.
Will we have the sheet behind that paper for the test?
But
Yeah, that one.
yeah, I haven't designed a quiz yet, but I think once you apply these a lot, uh, you like pick them up and learn them. Yeah, so I haven't made the quiz yet, but yeah, that's for a while. All right, so yeah, that's some fundamental examples. Again, so here's a quick recap. Okay, logarithms. You can express a exponent as a logarithm. Those are going to be inverses of each other. There's some inverse graphs. Okay. Okay. Common applications of these are anything that you're vastly changing order of magnitude. So like earthquake scales, you can express as a Richter scale number, right? Going from a mag 6 to a mag 7, that's like 10 times the intensity. Sound level intensity, right? You do that. Okay. If you want to say solve for how much time would money have to be in the bank earning interest to achieve some particular level, right? That's a good application too, right? Because instead of letting the time run, say how much money do I get, right? Say you're asking the inverse question, that could be a logarithm, right? Right, and then you have all these logarithms, adding, subtracting, multiplying, right, and changing base. Right? So it's all like, if you want to see a bunch more examples, again, I recorded over an hour and a half of examples. Those are on Classroom. I'm happy to walk around, help you guys out. And yeah, and of course, your next Alex assignment is open.